And now let me welcome the first speaker of today, Misha GLAZOV from Yofa Institute, who will be speaking about Exciton radiative decay and spin valley relaxation in van der Waals heterostructures. Misha, welcome.
Thank you very much, Nina. Thank you for the introduction. And first of all, I would like to thank the organizers of this very nice event. And I miss very much being in Clermont-Ferrand and meeting all of you in person. And this is really a drawback. But on the other hand, I do enjoy very much the conference, and it is fantastic and everything goes very smoothly. And indeed, in my talk, I'm going to speak about light-matter interaction in van der Waals heterostructures based on transition metal dichalcogenides. And this is a joint experimental and theoretical project we are doing together. Our theoretical team is from Yofa Institute. The theory has been developed by Anton Prasnichnych and Marina Semina and me. And we benefited very much from the collaboration with experimental group of Bernhard Urbaszek and Xavier Marie from Toulouse in France. And since we are speaking about van der Waals heterostructures based on two-dimensional transition metal dichalcogenides, we, of course, benefit from using the high-quality boron nitride, which comes from Tsukuba from Japan. So the plan of my talk is shown here. And basically, my talk consists of two main parts: about the control of exciton radiative lifetime in van der Waals heterostructures. There I will show both theory and experiment. And also I will speak about theory of controlling the exciton spin valley dynamics in van der Waals heterostructures. But before I go to the point of my talk, I will start with a brief introduction to the transition metal dichalcogenide monolayers and to the excitonic physics in these materials. And we have already heard some of the talks about these systems previously, but still I would like to remind you that here in this talk, we are focused on relatively novel semiconductor system with extreme two-dimensional properties, the monolayers of transition metal dichalcogenides, with main representatives being molybdenum disulfide, molybdenum diselenide, tungsten disulfide, diselenide, and telluride. And although these systems in bulk form are indirect bandgap semiconductors, in the monolayer form, you can make the monolayers using the Scotch tape technique exactly like you do it for graphene. So in monolayer form, these materials are direct bandgap semiconductors with very strong excitonic effects. So the symmetry and strong spin orbit interaction in these materials results in the fact that main physics, which will be of interest for us, takes place in the vicinity of the edges of the hexagonal Brillouin zone. So the Brillouin zone is shown here in the bottom, and there are 2 points, K plus and K minus, at the edges of the Brillouin zone. There you have more or less parabolic dispersion for the charge carriers and the direct bandgap. So the specifics of these materials is in the fact that depending on the light helicity, you can excite optical transitions in one valley, say K plus valley for sigma plus polarized light, or in the other valley, K minus valley for sigma minus polarized light. So together with optical orientation of electron and hole spins in these systems by circularly polarized light, you have also this famous spin valley locking effect, and you also produce the valley polarization of the charge carriers and the excitons. So what is very important here, since this monolayer is more or less well isolated from the environment, and also because of relatively heavy masses of the charge carriers, the Coulomb interaction between the electron and hole is very important. Actually, the optical properties in these systems are mainly governed by the excitons, bound electron-hole pairs, and depending on the environment and on the material, the binding energies of the excitons can be rather huge. So they can be hundreds of milli-electron volts, which are much larger as compared with conventional semiconductor systems. And although the Bohr radii are somewhat small, we know now that the one-year mode model describes relatively well the excitonic physics in these materials. And due to small Bohr radius and due to significant binding energy, these excitons have quite high oscillator strength. So the radiative decay rate of those excitons is the radiative broadening is on the order of 1 milli-electron volt, which translates to about 1 picosecond radiative decay time of the exciton. So you have really very strong light-matter interaction in these systems. And here I'm showing you the typical van der Waals heterostructure based on the molybdenum disulfide monolayer encapsulated in boron nitride with silicon dioxide and silicon substrate here. And this is the photograph of the structure, and this is the reflectivity, which was measured by our colleagues in Toulouse. And you can see very strong, very prominent excitonic resonances, the ground excitonic state, the spin orbit split excitonic state, and also the excited states, the 2s state and 3s state in the hydrogenic notations. So what is important here and what is really very clearly seen, that the light matter interaction in this structure is not only controlled by the optical response of the monolayer itself, but also by the multiple reflections of light in this heterostructure. And it results in particular in very strong enhancement of the excited excitonic state. So you can see that the feature in the reflectivity related to the 2s exciton is almost as strong as for the ground excitonic state. Although the oscillator strength, if you just calculate it for the pristine monolayer in the vacuum, will be different by a factor more than 10. So this is the specifics of the van der Waals heterostructures, which allows one to change significantly optical response of the monolayer. And of course, there are a lot of experimental realizations of different systems. There are the strong coupling of excitons in 2D semiconductors with photonic modes have been demonstrated both in purely dielectric systems and also in the hybrid systems, which include metallic structures, also with plasmonic resonances. And in these systems, you can reach very high values of the vacuum Rabi splitting for the excitons. But now I'm coming back to a very simple question, to the question about radiative decay rate of the exciton in a monolayer embedded in the van der Waals heterostructure. I have already tried to convince you that optical response of these TMD monolayers is controlled by the excitons. And we would like to address the question how the light propagation in the van der Waals heterostructure affects the exciton spontaneous emission. And here I'm showing you again the experimental sample our colleagues in Toulouse used. This time it is molybdenum diselenide monolayer. So basically the physics is the same for all the materials I mentioned. They share the same properties. Of course, there are quantitative differences related to the different band gaps, spin orbit energy, exciton binding energy, and so on. So this is the exciton. So we will study exciton in monolayer of molybdenum diselenide this time. Again, we have the top and bottom hexagonal boron nitride layer, silicon dioxide, and silicon. And some of the samples were made with the steps of the boron nitride. So you can see that the thickness of the bottom boron nitride layer is different in the different parts of the sample. And that is why if you look just at the white light reflectivity, you will see a kind of rainbow because of the different interference condition for the light. And of course, in this sample, you can see very narrow exciton and charge exciton resonances, which more or less approach the radiative line width of about 1 milli-electron volt. So what our colleagues did, they made experiments on time-resolved photoluminescence, and they measured the radiative decay rate of the excitons for different thicknesses of the hexagonal boron nitride layer. So trying to model different kind of van der Waals heterostructures. Actually, the first puzzle which appeared is clearly seen here on the top panels. There for two samples, there the monolayer was placed actually in the node and in the antinode of the electromagnetic field in the structure. There is almost no difference in the decay time of the photoluminescence. At the same time, by contrast, the rise time of photoluminescence is very different. And this is a particular feature of the strong light matter interaction in those structures. There, the shortest decay time is the radiative decay time of the exciton. That is why it controls the rise time of the photoluminescence. While the relaxation of excitons from the reservoir down to the emitting state controls this much slower photoluminescence decay. Now, by measuring this rise time in various samples, the various thicknesses of the boron nitride layer, you can see these points. You can get the radiative lifetime of the exciton as a function of the boron nitride thickness. And also you have very good correlation between the inverse radiative lifetime and the line width of the photoluminescence spectrum. So, okay, one can see a pronounced modulation of the radiative lifetime in the experiment. So what about the theory? How we can quantify this effect? Okay, I will just show one slide with very basic physics because I do not want to go into the details here, and I believe that most of you understand this effect even better than I do. So you can consider exciton just as a dipole which emit light, and its radiative decay in the semi-classical approximation can be considered just as a self-consistent interaction of exciton with induced electromagnetic field. You can speak also about so-called radiation friction, because due to the emission of radiation, of course, dipole loses the energy. Now, if you have somewhere a mirror, or you put your dipole in a cavity, then the total field which is experienced by the dipole is the emitted field, and also the field which was reflected from the mirror or from the cavity. So the dipole emits the field, then it gets reflected from the mirror and goes back. And that is why if you calculate the dynamics of the dipole, dynamics of its decay, then you get this additional factor, 1 plus R. There R is the complex reflection coefficient of the mirror. And its real part describes the enhancement or suppression of the decay rate, and can be also associated with the Purcell factor, which is usually invoked for the description of the modulation of the radiative lifetime for the dipoles in the cavity. Of course, you can make a microscopic theory by considering the optical properties of this structure within the transfer matrix method, or you can use the Fermi-Golden rule with exactly the same result. So anyway, if you change the thickness of the boron nitride layer, you can change the interference condition for the light here, and that is why you effectively change the radiative decay rate of the exciton. And then, of course, you can expect the oscillatory behavior, since you have the propagating wave here. If you change the thickness, then you can see the oscillations of the radiative lifetime. And this solid curve here is our theory, which matches the experimental data very well. And you can see that actually the modulation of the radiative lifetime reaches a factor of 20 from 0.5 picosecond and probably even shorter up to about 10 picoseconds. And you can also infer the free space radiative lifetime of exciton in this structure to be 2.7 picoseconds. So this is the key result. You can have a van der Waals heterostructure, and you can have a significant Purcell effect on excitons in this heterostructure. And then about the same time, there were several other papers which came essentially to the same conclusion. So, okay, this was about the radiative lifetime. Now I'm going to talk about spin valley dynamics of excitons. And the idea is very simple. If you shine circularly polarized light, as I explained before, you induce transitions in one valley only. You create the electron-hole pair, say here or there. And then we know that for excitons, the main cause of depolarization is the long-range exchange interaction, which is related to the exchange between the charge carriers by virtual photons. I will explain it in one slide. And of course, the question is very simple. How does the monolayer environment affect the valley depolarization? How does the environment affect the spin valley dynamics? So to explain the physics in a little bit more detail, I will just show this very simple cartoon, how the long-range exchange interaction works. So you excite the electron-hole pair here, the electron is here, unoccupied space in the valence band is here. And now you take into account the interaction of this electron with one of the electrons in the valence band in the other valley, like this. This is just the Coulomb interaction, the exchange part of it. And then the following process happens. These electrons, due to interaction with that one, goes to the valence band, and that electron gets promoted to the conduction band, like this. And now you can see that exciton flipped its value, or flipped it pseudospin, so you can have the Welle depolarization of the excitons due to the long-range exchange interaction. And you can see that this process is a kind of virtual annihilation of exciton and virtual creation of exciton. So it is indeed related somehow to the electromagnetic waves propagating in the structure. The Hamiltonian for the exciton is shown here, and for the suspended monolayer, or for the monolayer embedded in the homogeneous dielectric, the Hamiltonian is actually linear in the wave vector, and its angular dependence is described by the second angular harmonic, since you need to flip the spin of one. And the splitting between the eigenstates of the exciton in the monolayer are linearly polarized, with the microscopic dipole being either parallel or perpendicular to the wave vector. So the splitting is controlled by the radiative lifetime of the exciton. Now, if you consider the van der Waals heterostructure, which consists, say, of the hexagonal boron nitride, silicon dioxide, and probably also of the top layer of HBN and also silicon, then compared to the radiative emission, the situation here is a bit more complicated. For the spin Welle dynamics, we are interested mainly in the excitons which have quite high wave vectors outside of the light cone. And in this case, these excitons produce electromagnetic field which decays to the both sides of the monolayer. And that is why if you change the thicknesses of the layers in the structure, you do not have the propagating waves, but you rather have decaying waves. And that is why you can expect that the modulation of the exciton longitudinal transverse splitting will be monotonous rather than oscillatory. And actually, this is confirmed by the microscopic calculations which were carried out by Anton Prasnichny, the master student at Yoffo Institute. So I'm not going into detail explaining all the details on these plots. This is the expression for the exciton LT splitting in the van der Waals heterostructure. It can be also approximated for sufficiently high wave vectors as a linear function. As you can see, there is a good agreement between analytical asymptotes and numerical calculation. But effective dielectric constant, which enters here, depends on the thicknesses of the layers and also on the wave vector of excitons. So in short, if you add some dielectric environment around the monolayer, of course, you screen the exchange interaction. You screen the long-range exchange interaction, you suppress the long-range exchange interaction, and you can expect that you make the spin Welle relaxation of excitons longer. And indeed, this qualitative effect is confirmed by quantitative microscopic calculations. We use the density matrix approach and pseudospin approach to study the exciton spin Welle dynamics. And I'm not going again into all the details of calculations for different heterostructures, different temperatures, and so on. So probably the key result is shown here. You change the thickness of the cap layer of hexagonal boron nitride, you increase the thickness, and then you see the increasing of the spin or Welle depolarization time of excitons as shown by these curves. And overall, you can also expect significant enhancement by the factor of about 5 or 7, depending on the structure studied. So I think that I'm coming to the end of my talk. So the intermediate conclusion is very simple. Encapsulation of the monolayer into hexagonal boron nitride screens the long-range exchange interaction and slows down the Welle depolarization of excitons. And although the radiative decay of excitons and the long-range exchange interaction between electron and hole have the same physical origin, they are related to the self-consistent coupling of exciton with the induced electromagnetic field, the dependence of the radiative decay rate and of the long-range exchange interaction on the thickness of the surrounding layers is different. So for the lifetime and for the radiative decay, this dependence is oscillatory because exciton within the light cone produces propagating waves. And for the exchange interaction and corresponding spin Welle decay time, the dependence is monotonal because we are dealing with excitons outside of the light cone, which produce the decaying waves rather than propagating ones. So thank you very much for your attention.
Thank you. So Alexei has a question already. Please, Alexei.
Yes, so dear Misha, these flakes of TMDC, they are small, and
yes.
edges may play a role. In particular, the wave vector conservation in plane is broken if you are not that far and you are never very far from the edge. And from this point of view, you know, all this story of light cone, outside light cone, inside light cone, is it really valid? And maybe experimentally they can check if for example, the decay time of photoluminescence that is governed by this relaxation from reservoir is dependent on the position of the spot. Because if you move it to the edge of the flake, then all these relaxation processes must be accelerated, and then you should see the faster decay if the model of you know, that you developed is valid.
Alexei, thank you. So partially, I'm ready to agree with you. The samples are not that large, but not that small. They're about 20 micrometers. And I think in the experiments on the radiative decay, the efforts were done to illuminate, to focus the light quite tightly and not to eliminate the edges. And there is very good correlation between the decay rate and the line width of the luminescence for many positions at the samples. So it was checked. But of course, you are right that in the vicinities of edges, the physics is very different. But unfortunately, I believe that it is mainly caused by the defects which are in the vicinity of the edges. Not only because the edge itself, even the ideal edge, breaks the momentum conservation, but just because there are more impurities or some other structural defects. That is why, indeed, and we know it, that something happens in the vicinity of the edges.
Thank you.
Guillaume?
Okay, so quite, since we are on this slide, so in the quite same way with respect to Alexei, the line width is, your conclusion is that experimentally it is dominated by radiative effect and not by disorder or something like this.
Mainly, yes. At least for the samples, there the radiative rate is shortest, then the line width is largest. So then it is about, say, 2 milli-electron volt. It is mainly due to the radiative process. If it is about 1 milli-electron volt, there could be some degree of inhomogeneous broadening. And also, in fact, in experiment, they collect light which doesn't go exactly along the normal to the sample, but from some angle, due to the finite numerical aperture of the objective. That is why there could be other mechanisms of broadening. But mainly the line is homogeneously broadened due to the radiative process.
Are there more questions?
Yeah, I think that there is a question from Ronan, if I'm not mistaken.
I don't see any hands raised, but
on the screen.
Press the button, Ronan. Please ask your question.
Oh, yeah. Okay. So Misha, very nice. Have you considered these calculations also for interlayer excitons?
Not yet. In principle, everything can be done. But for interlayer excitons, we expect that, of course, the light-matter interaction is suppressed. The radiative lifetimes will be much longer. The effects will be similar, but I'm not sure that they are now directly accessible experimentally, because even for trions, the radiative decay time is on the order of 10 picoseconds. There is almost no modulation. I can try to show you. This. So for trion, or even longer. So for trion, the lifetimes on the order of hundreds of picoseconds, and there is almost no dependence on the thickness of the boron nitride layer. So, and this is clear because this time is too long.
Thank you.
Are there further questions? We still have about 5 minutes. Ivan, please.
Yeah, hello, Misha. Sorry for being dark now.
And that's okay.
The best I can afford at the moment. So I have a question. Can you please be more specific with the configuration of the light which you use in the theory and experiment? So it's not a cavity, it's just some
No, it's not a cavity. So let me try to show the structure once again. This is the monolayer. Yeah, this is the monolayer. And it is just surrounded by boron nitride. The top layer is very thin. It's about several nanometers, probably 2 or 3 or 5 nanometers, and it plays no role, at least for the modulation of the radiative decay time. And the bottom layer is significantly thicker, so its thickness changes from, say, 100 to several hundreds of the nanometers. So you can go through half the wavelength and 1.5 wavelength in the media. So this is the structure. And now if you change this thickness, you change the interference condition. In fact, you may say that you just modulate the reflectivity of this mirror, which is made by the hexagonal boron nitride, silicon dioxide, and silicon. And if you change the thickness of this mirror, then the reflectivity of this mirror, you change the Purcell factor, and then you change the radiative decay rate of the exciton.
Yeah. So this is actually what a bit surprised me here. So usually Purcell effect sort of puts lifetime of excitons because of presence of light, but it seems to be no surprise. So what is special here in this setup, as for example compared with cavities where the same thing happens?
No, Vanya, of course there is nothing very special. Basic physics is exactly the same. You put your emitter in a media with different properties, with different electromagnetic field per photon, and you get different lifetime. The specifics of van der Waals heterostructures based on TMD, that you can really make it experimentally without complicated cavity, and you can observe this modulation more or less in one sample, just by using this nice, they call it rainbow sample, with different thicknesses, with different steps. That is why you can tune your light matter interaction. But basically, of course, we just get another confirmation that basic physics, Maxwell equations, and simple quantum mechanics for exciton radiative decay, it works.
It works. Okay, thank you very much.
Nothing special.
Thank you.
Guillaume, you should turn on your microphone.
Yes, so thank you very much again, dear Misha, because by many aspects, your talk has a lot of similarities with the one I made at PLMCN 0 in Senecter in, 20 years ago. It was really some quantum wells placed in this, heterostructures, Bragg conditions, and so on. This reflectivity of the quantum well, everything was, by many aspects, very close. So, well. As you said, it's perpetually.
Thank you. Thank you. We can go back to this point during the session, Polaritonics in Clermont on Friday.
Yeah. Okay.
So we are actually, we used all the time. Thank you very much again, Misha, also for being on time. And I will
I think that I need to stop sharing my screen, otherwise I will block next talks.